I will begin. Dear Father, we thank you for this day again, Lord. I thank you for these students. I just pray that you'd bless this class as we just try to understand a little bit more about your creation together, Lord. In your name I pray. Amen. Okay, so this is, I believe this is lecture 21. I said last one was lecture 20, right? So I think successor principle, we should be okay. Let's see here. So lecture 21 is on the Sylow Theorems. And so this is, of course, section 8.4 in your book. All right. And so let me just kind of set the stage here. It all goes back to Lagrange's theorem. So what did Lagrange's theorem say? It said if H is a subgroup of G, right? Then what? The order of H must divide the order of G, right? However, conversely, the direct converse to that, though, if M divides N, which is equal to the order of G, then that does not imply, right? That does not imply that there exists a subgroup H of G with the order of H being the divisor of M, divisor of N, say M, right? So, when you make a statement like that, you're obligated to give some specific counterexample, right? So our counterexample, our go-to counterexample of the converse of Lagrange's theorem failing is A4. A4 has order 12, right? And there does not exist a subgroup of A4, right, with the order of H being 6. Now, I'm not sure I've actually proved that in its entirety in lecture. In fact, I'm pretty sure I haven't. But it's certainly been in your reading, right? So this is the counterexample to Lagrange's theorem's converse, right? But there's something kind of suspicious about this divisor. This divisor here is what? What kind of divisor? This is a divisor of 12, right? Surely that's true. But what kind of divisor is it? Is it a prime divisor? No, this is a composite divisor, right? It's formed by 3 and 2. And it turns out that if you insist that the divisor is not composite, if you insist that the divisor you're talking about is a prime power divisor, then in fact the converse of Lagrange's theorem is true. In other words, if you have a prime to a power k, and it divides, so here's the, if we have that a prime to the power k divides the order of the group, then that in fact does imply that there exists H, a subgroup of G. Well, this is worthless. With the order of H being equal to p to the power k, p prime. P will be a prime in this entire lecture, let it be known. I'm not going to write that 30 times, all right? And guess what? G is going to be a group. At no point will I use G that's not a group. So if I don't write it, you'll forgive me. So this strengthening, well, let's see. What do you want to call this? It's a, it's a weakened form of the converse to Lagrange's theorem, but this was discovered by, this is one of Sylow's, this is Sylow's result. Now, to be more careful, Sylow's result actually was that if the order of G is equal to like m times p to the n, where p does not divide m, right? He actually proved this case in the case that the prime power was sort of maximal and everything left, and everything left over. It was that he proved that there exists a subgroup of order p to the n. And more specifically, Sylow proved this for permutation groups in about 1872. I have to look at my paper. I wasn't around then. And then, interestingly, the theorems we'll actually go over today were first established by Frobenius in about 1887. Frobenius is a very important figure in 19th century mathematics. He kind of came along and took things people did in a special case here or there, and he just did them for like arbitrary integers. He did a lot of that. A lot of what we call linear algebra is probably due to Frobenius. I mean, you could say, well, it's due to Cayley, or pick your favorite earliest 19th century mathematician. They did the case for like n equals to 3 or 4, and so sometimes we'll credit to them, but later Frobenius came and did it for n, So what we actually present in linear algebra, a lot of it's due to Frobenius, I think. Okay, so here's theorem 1. Section 8.4. It says the following: let G be finite group. All right. If P is prime, said I wasn't going to write it. Oh well, it's too late. If P is prime and P to the power K divides the order of G for some K greater than or equal to 0, then G has subgroup of order P to the power K. All right. I think it's worthwhile for us to go through the proof of this because it's rather pretty, and I think it also helps to drive in the point that you guys should learn the class equation and think about using it for certain kinds of proofs. Right. So here it is. First of all, K equals 0, dumb. Okay, so we'll suppose K is greater than or equal to 1. And the proof is going to be by induction on the order of the group. All right. So the first few cases, think about the order of G equals to 1, 2, or 3. Is this theorem true for those cases? For the trivial group, the only thing that that has nothing to do really. For 2, you have an element of order 2. So, I mean, you can check that for P equals 1, 2, and 3, this theorem is true. So we'll proceed by induction then. And the critical tool for us is the class equation. So we have for A1 through AN with non-singleton conjugacy classes, the following, right? We know that the order of G is equal to the order of the center of G plus the sum of what? I equals 1 to n of the index of G by the centralizer of A sub I. I'm sorry, by the normalizer of A sub I. Right. So there's really kind of two cases to consider. The one case to consider would be that suppose PK divides some. So what are we assuming? By the way, I should probably say that. Maybe right at the start of the proof. What are we assuming? I mean, this is typical of a proof in the book, right? He won't restate the assumption of the theorem in the proof because it costs money to print books, right? I mean, we're assuming that p to the k, right, divides the order of g. That is assumed. Okay, so suppose p to the k divides the order of n of ai for some I, right? Then, as the normalizer of ai is a, the order of that is less than the order of g. Can you guys tell me why? Given our assumptions, why should the order of a, what are these? These are non-singleton conjugacy classes, right? What do those conjugacy classes do? Yeah, they partition the group. So what would, if the normalizer, if n of ai was equal to g, what would that mean? Yeah, there'd just be one conjugacy class. Everything would be in the center, right? That n of ai would be the center of g. But we're assuming that a1 through an are non-singleton community. I mean, I guess if there are no non-singleton conjugacy classes, right, then this piece is gone, and we have g is equal to its center. Is there a different argument we can give in that special case? I will go on then. So as this is less than g, that implies we can find a subgroup of what? Order pky by induction, right? By the inductive hypothesis. Let's agree that if g is not equal to its center, it should be relatively clear that the normalizer of ai has to be a proper subgroup of g, which means we can apply the induction hypothesis, right? There must be a separate argument that we can give if g is equal to its center, right? If g is abelian, there must be a different argument that we could give. Okay, so I'm going to go on. So there exists a subgroup of order pk by the inductive hypothesis, right? What's the other case then? What's that? I can't hear you.
And the cardinality of n of ai is not divisible.
Right. So p to the k does not divide n of a, the order of the normalizer of ai, for each I greater than or equal to 1, right? So then what? Remember that we have p to the power k divides the order of g. And what else do we know? We know that the order of g is equal to what? It's equal to the cardinality of the normalizer of ai, as you called it, the size of that subgroup, times its index in g, right? We're assuming g is a finite group. So what's that say? Just think about primes. What's that mean? If p to the k divides this, right? So p to the k, sorry, over here. P to the k does not divide this, you know? What's that say about this here then, by basic number theory? I mean, prime factorization of integers. A little bit too strong. See, it could be that p to the k minus 1. You see, if I had, I mean, this could have a divisor of p to the k minus 1. If this had p to the k minus 1 in its factorization, then I can't find a p to the k over here. Right? So like there's p to the k in here. There has to be at least one p over here to spoil the divisibility of that factor. So all we get from prime factorization is that p divides this. There has to be at least one prime factor over there. But I thought the same thing as you, Alan, when I first looked at it. I was wanting it to be p to the k, but that's because I'm not a very good number theorist. But anyway, okay, so then what? Then we can go back to the class equation, right? What's the class equation tell us? So you look at this, right? What do we have? We have p to the k does not divide that. Well, I'm sorry, but what does divide that? Right, so if I call this thing Pac-Man, right? And if I call this thing, well, Ghost, we have, of course, we have p divides the Ghost, right? And p divides the Pac-Man, because if it divides each thing in the sum, this holds for arbitrary I, so it holds the sum of things divisible by p is again divisible by p, right? So that means that by the class equation, p must divide the order of the center, right? But the center is abelian. So by Cauchy's theorem, what? There has to be an element of order p, right? So that implies that there exists A in Z of G with the order of A equals to P. So construct what he calls K, the subgroup generated by A. This is a subgroup of order P, which is normal in the group. See, this is a subgroup of the center. So we have K as a normal subgroup of G with the order of K equals to P. Again, this is by what I should actually write it. Cauchy's theorem, right? Then what? So you get a normal subgroup, so you can look at the quotient, right? So consider, if we look at G mod K, or the factor group of G by K, that has order what? That has order G over order K, right? Which is what? That's 1 over P times order G, right? P's prime, so this is less than order G, which means the factor group G by K has order, smaller than G. Why am I writing that again? I just have that up here, duh. Hence, allows us to what? Apply the induction hypothesis, which is what? That a group of order whatever has an element. If a prime to some power divides the order of the group, then there is a subgroup of that order. So what prime power divides this? Exactly. So p to the k minus 1 divides the order of G over K. So that implies that there exists, let's say, H over K, a subgroup of G over K, with the order of H over K equal to p to the k minus 1. and H is a subgroup of G, okay? What I'm claiming then, by the way, guys, is that every subgroup of the factor group appears in this way. If you have a subgroup of a factor group, you can understand it as appearing from the quotient of a subgroup of the group by the thing you're factoring. So there's no, that's not, anyway, but I think that's something we proved earlier. If it's not, it's something we ought to prove. Anyway, so once you have that, what's that give us? What's the order of H? The order of H divided by the order of K is equal to p to the k minus 1, which implies that the order of H is what? P times p to the k minus 1. Yeah, p to the k. So there you go. That's a subgroup of order p to the k. And that finishes the induction. It's by strong induction, I guess. I mean, not I guess. It's definitely by strong induction. So I thought I should write that out for you guys because I think it's important to see this written out. If nothing else, so you guys can appreciate, like I said, that the class equation is so important to our thinking here. I won't prove the rest of the results. I just want to talk about them with you. I might have a proof or two in here. I forget, but that's the one I wanted to make sure we went through line by line. All right. Here we go. So we already went through this proof. So, like I told you guys, oh, come on. Yeah, you somehow can't. Oh, it's, you know what it's going to be. You got it? Okay. So like I said, this is actually a special case of the theorem we just proved here. Right? This was for p to the power k, where p to the k is any divisor of the order of the group. Right? But anyway, well, anyway, this is what Sylow actually proved a special case of that. Let's look at an example. So D3, you can understand a lot from D3. I should mention down here this language before I look at that example. If G has order m times p to the n, and p is not a divisor of m, p doesn't divide m rather, then H is a subgroup of G with the order of H being p to the n. That's called the, I shouldn't say the, I should say because it doesn't have to be unique. It's called a Sylow P subgroup. All right? There can be more than one. In fact, if you look right above, here's an example. So in D3, we have two kinds of subgroups, right? Well, four, I guess, but two of them are stupid, right? 1 and D3 itself, boring. I guess it's not boring, but whatever. Anyway, so H, this guy, is the unique Sylow 3 subgroup, right? And in contrast, this down here, these are all Sylow 2 subgroups. So yeah. So in this case, the n is just 1, right? So it's I guess it's more exciting when n is more than 1, but you know, still examples. Now, do you guys remember what we know about? Well, let me one thing at a time here. Let me go on. Example 2. If G is a finite abelian group, if you have P is a divisor of the order of G where P is prime, then he defines this G of P to be A in the group such that the order of A is P to the power K for some K greater than or equal to 0. So let's see here. So it could be like you have P could be 3, right? So this would be the collection of elements of the group that have order what? Like 1, 3, 9, 27, and so forth, whatever it happened to be. So it's not just the p to the power k things. It ranging from the identity up to the maximum, so it collects together everything, all of the elements of the group which have prime power order, whatever that prime might be. So this contains every. Do you guys remember what's a P subgroup? We talked about this another day. What was a P group? Okay, so all the elements are powers of, so this is pretty much by construction a P group, right? Yeah. So every element in the group is some power, has an order which is some power P. Okay. So the Klein 4 group is an example of this, right? It's the prime is what, 2? Everything has 2 to a power order in the Klein 4 group. So anyway, that's called the P primary component of G. This is, by the way, three of you said that you were interested in Math 422, but I wonder, search your heart, search your DCP. Think about the courses which are offered next semester. Is it accurate that you don't want to graduate next semester? Because that was what it might mean if you decide to not take 422, right? I mean, it could be that you need to take that for graduation. I'm just saying. You should think about this. Actually think about this, because if you're assuming you're going to take a course which we offer this semester, next semester, you'd be wrong, right? So you have a choice, right? Either 422 or what's the other one? 401, which no longer exists, so 411, right? When is 411 offered? Right now, right? When is 311 offered? Spring, yeah, that doesn't help you though, does it? Because 311 will not substitute for 401. Yeah. There's a calculus here you need to think about. It might be that you should be in 422 next semester. And if you are such a person, we are going to reschedule the class, right? So you'd like to figure that out sooner rather than later so that you can participate in the selection of the time, right? Because, if we decide it's going to be Saturdays at 3 in the afternoon, and you come late to the course, I'm sorry, that's the bed that we already made. You got to lie on it, Just saying. 422. It's just a friendly neighborhood reminder that you should think about whether or not you need to take 422. I will stop using valuable class time on such nonsense. All right, anyway, so so in 422, we will prove, among other things, that every finite abelian group is isomorphic to the direct product of its primary components. That means that if you have a finite abelian group, you can write it as the direct product of its distinct Sylow P subgroups. So these Sylow P subgroups are actually kind of important. They have a lot to do with how you break apart a given group, a finite abelian group, into its sort of fundamental building blocks. Sylow P subgroup, let's call it P with a foot, is a finite of a finite group G is a P subgroup, right? Means every element of it has prime power order of maximum possible order, right? Furthermore, if you look at it, if you have a Sylow P subgroup and you conjugate, right? Then because the size of the conjugate is the same as the size of the subgroup, they have the same size, right? So that means that this is a Sylow P subgroup, then that's a P subgroup. So, and conversely, you can prove that, in fact, every Sylow P subgroup is reached in this way. If you have one, all of the others can be reached by conjugation. So this is actually very neat, because what that means then is, well, that theorem, theorem 2, leads us to Sylow's second theorem, which says that if you have a finite group, then any two Sylow P subgroups are conjugate. I think I just said that, actually. That is Sylow's second theorem. And the corollary to that is actually very, very interesting. A Sylow P subgroup in a finite group G is normal, right, if and only if it is the unique Sylow P subgroup. Think about that. So what does it mean to be normal? It means that when you conjugate the group, you get back the group again, right? But on the other hand, all the different Sylow P subgroups are related by conjugation. So if there's just one Sylow P subgroup, that means that when you conjugate the subgroup, you get back to the group again, which is to say it's normal. So this is very neat, because this means that there's a connection between the Sylow P subgroups and normality. I just wrote them again and gave them some sort of unnecessary bubbling. Again, any two P subgroups are conjugate, and a Sylow P subgroup is normal if and only if there is just one of them. And if you look at our D3 example, you can see this in action, right? D3, we had 3 Sylow 2 subgroups. These are not normal. If you conjugate one, you get to the other. In fact, we've looked at this the other day. These 3 conjugate, if you take conjugation, you know, by, I think A, it gets you to here, and by A squared, it gets you to there, or something like that. I forget exactly, but anyway, maybe vice versa. But these are related by conjugation. You can find an inner automorphism which will map one of these to the other. On the other hand, this guy has index 2, right? Therefore, it's normal. And that illustrates the fact that we should expect this because it is the unique Sylow 3 subgroup in D3. It's kind of neat, right? There's this Frattini character. He tells us something else. I will not prove it, but I'll state it because it's interesting. If you have a normal subgroup in G, and if you have P as the Sylow P subgroup of H, all right, then you can write G as the product of H and the normalizer of P and G. So this means we can build the group as a product if we have a normal subgroup and its P subgroup. So there's some kind of connection between, you know, building groups from products and these Sylow P subgroups. The proof of this is not that hard. It basically goes back to the section 8.1 in chapter 8, where we had those products about building groups from products of subgroups. This is also very natural, these results here. Point number 1 says if you've got a normal subgroup of G, then a subgroup of K is the Sylow. What do the Sylow P subgroups of a normal subgroup of a group look like? They are formed by intersecting a Sylow P subgroup of the supergroup in which the group fits. So if you're looking for the Sylow P subgroups of a subgroup, they have to appear as intersections of the P subgroup of the larger group in which K is fitting. It's a very, very natural result. Just think about it. What is the most natural thing you could expect in terms of how you would construct the P subgroups of a normal subgroup. I'm saying subgroup an awful lot. Subgroup K. I need another word for subgroup. Should just call him Bob. A Bob of G mod K is a Sylow P Bob of G mod K if and only if it has the form pk divided by k, where P is a Sylow P sub Bob. Oh, I'm sorry, Bob of G. Excuse me, I'm misusing Bob. But also, so if you're looking at a quotient, then this is how the Sylow P subgroup of a quotient has to appear. It has to appear as the product of the Sylow P group of the supergroup by K, like this. This actually was a little bit tricky to prove. Number 1 didn't look too bad. But anyway, again, I'm just trying to share these with you. Sylow's third theorem, this one I'd actually like you to learn. The last 2 ones I just did, those are kind of informational, but Sylow's first, second, and third theorems, these are things you should probably try to learn. Right? I might ask you a question about them. So here's Sylow's third theorem. And notice I didn't say that I expect you to be able to prove them. I mean, the first one, the one I did here, I might ask you something about that because we actually went through the details. But the second and the third, maybe not. I don't know. Let me stop talking about the test. All right, so let G be a group of order p to the mm, where p does not divide m, and n is greater than 1. And n sub p, what is this? This is the number of distinct Sylow p subgroups of G. All right? Then we have these three things. First of all, the number of p Sylow subgroups of G is congruent to 1 mod p. It's weird. The number of p subgroups, Sylow p subgroups rather, must divide M. And 3, the number of Sylow p subgroups must be equal to the index of G by the normalizer of P. This is supposed to be P with a foot. I try to put a foot on that, where P with a foot is any Sylow p subgroup of G. And this is Sylow's third theorem. And it is a deep and powerful theorem in terms of what it does for chasing down possibilities of group questions. Here's an example of its power. Here, I'm sorry, I'll go back up. See, you guys are still copying, sorry. So suppose P and Q are primes, then no group of order PQ is simple. Now, being mathematicians, we have perversely defined simple to have a technical meaning, right? So for non-mathematicians, what's simple is not simple, right? Because it involves all kinds of crazy math hieroglyphics that, but really, I mean, what does it mean? Simple, if it's simple, that means that the only normal subgroups are one in itself. Another way of saying that is a simple group is one which does not have any interesting factor groups, right? If a group is not simple, that means that there exists an H between 1 and G. And so if that's a normal H, you can form G by G mod H, and that's an interesting factor group, which contains partial information about the group, but on the other hand, squashed other things out to 0, right? I mean, this is the theme of the last few sections in the book we've looked at, is that by looking at factor groups, you can gain information about the group indirectly. Anyway, if P is equal to Q, then the order of G is P squared, which means that it's abelian, and it must be this or that. That was a theorem in section, I think, 8.1. Either of these, like if you think about the cyclic group of order P squared, if you look at what's the order of P squared? Excuse me, what's the order of P? Is it, if I'm looking at, like, let's see, let's make it more specific. In Z25, what's the order of 5? It's 5, right? Which means that in this, there is a subgroup of order P, which is not 1, and it's not the whole thing, and it's abelian, so it's a normal subgroup. So this is not simple, and that's also not simple. So that means that in this case, not simple, right? What are the other, so that we didn't need Sylow's third theorem for that. What if the primes are not equal? Then you can suppose without loss of generality that P is larger than Q. All right, Sylow's third theorem tells me that the number of Sylow P subgroups is congruent to 1 mod P. We also have that the number of Sylow P subgroups has to divide the Q, because Q is like the M. It's what's left over in the order of G. And so if you think about that, that forces us to put n sub p equal to 1. So there's a unique Sylow P subgroup, which means that it's normal, which means we've shown that the group's not simple. Not too bad, huh? So that's, yeah, that's marginally impressive. This one, I think this should sell you on how Sylow's theorems are useful for specific questions about groups of finite order. Show every group of order 175 is abelian. This is a terrifying question about 3 weeks ago, right? Without this technology, this would be like a really, really imposing question. I mean, I'd have to think really hard about it. I don't know if I could. I doubt I could. But here's the solution. 175 is 7 times 5 squared. So you can look at Sylow 5 groups and look at Sylow 7 groups. And if you look at the Sylow 5 groups, they have to have such the number of them divide 7, and the number of Sylow 5 groups is congruent to 1 mod 5. That implies that N5, the number of Sylow 5 groups is 1. So that means that there exists a unique Sylow 5 subgroup, and it's normal. Almost the same argument works for the other divisor, 7. The number of Sylow 7 groups has to divide 25. So that means that the number of Sylow 7 groups is either 1, 5, or 25. But we also have to have that number is congruent to 1 mod 7. Is that congruent to 1 mod 7? Yeah. But is that congruent to 1 mod 7? No. What's this congruent to mod 7? 4, not 1, right? So that forces us to have n sub 7 equal to 1. So there exists a unique Sylow 7 subgroup Q, normal subgroup of G. But we can count. That's 25. That's size 7. So altogether, we have that. By the way, also, these intersect at 1 because they have relatively prime orders. And consequently, the order of the group is the order of the product of the subgroups, both of them normal, intersect at 1. So going back to the first section in Chapter 8, this gives us that G is isomorphic to the Cartesian product of P and Q. That's a billion. That's a billion. So G is a billion. Yeah. So, and the book, to shove your face in it, like the book has like 2 more examples past this that just make you go, whoa. I won't even cover them. And it also has a few more theorems about like products of primes, all right? And a little bit of discussion about famous things that have been done by Burnside and others. And, you know, there's a lot more we could say about groups. But this is kind of where I stop, in some sense. I am now going to enter Jeopardy mode. So if you put everything we've put together, you can summarize, and we've given arguments, specific arguments to affirm part of this. But here it is, up to isomorphism. These are the groups. Order 1, Z1. Order 2, you got Z2, up to isomorphism. Order 3, Z3. Order 4, you got the cyclic group of order 4, or you got the Klein 4 group, Z2 cross Z2. Order 5 is prime Z5. 6, you got Z6, and you also got S3. So order 6, you got 2 different kinds of groups. You got your abelian one, you got your non-abelian one. S3, of course, is isomorphic to D3, as you may recall from the test. Sorry, I should stop doing that. Z7, well, that's prime, so that's just the cyclic group of order 7. 8, 8's interesting. Weird stuff happens at 8. You got your Z8, you got your Z4 cross Z2, you got your Z2 cross Z2 cross Z2. You got your octet group, you got your quaternion 8 group. Them's your choices. Up to isomorphism, there's 1, 2, 3, 4, 5 distinct isomorphism classes at order 8. At order 9, these are your choices. There is no non-abelian group of order 9. But abelian, you got this and that. Order 10, you got 2. You got Z10, you got D10. In fact, whenever we have order 2 times a prime, we actually proved that if the order is 2 times a prime, then you've either got Z mod the order or you've got the dihedral group of that order. Right? That's the result we did actually prove. 11, prime again, so just cyclic. 12 is weird. It's got this, that, and you got your A4, you got your D12. And this, we haven't talked about. This is the semi-direct product. This is a section in Chapter 8 I have been merciful to have not covered for you this semester. Wait a minute, I wasn't being merciful. I was cheating you out of your education. You should be upset with me. I did not cover semi-direct products. How dare you, sir, you should say. Get to that Friday, right? No? Okay. Just checking. But yeah, that's a semi-direct product, which is kind of what it sounds like. It's partly direct, but partly not. There's more. Here's 13, 14. We proved this one. 15. So the prime, that, I don't remember. Look at this, 16. Yowzers. But anyway, this is from Dummett and Foote, which, you know, is kind of like an encyclopedia of undergraduate abstract algebra. Your typical undergraduate abstract algebra book is what, 400 pages maybe? 300? What's yours? 500. Yeah, this is a little bit thicker than most. It's good. Dummett and Foote's about 1,000 pages. Yeah.
Why is Z15 not having it? Why is order 15 only one?
There's also, well, you could rewrite it as Z3 cross Z5, but 3 and 5 being relatively prime. it's a cyclic group. So up to isomorphism, Z15 is Z3 cross Z5.
Is that true from prime?
You could write Z10 as Z2 cross Z5. It goes back to that theorem we had, which is that if you have two groups that have relatively prime order and they're both cyclic, then their Cartesian product is a cyclic group, which is the product of their orders. And we got the converse direction to that more recently. So we have proved part of this, right, but not all of this table. But there's a lot more known about groups. Like the classification of arbitrary finite groups is very difficult. I don't know how far that's gone at the moment. But if you set your sights a little bit lower and say, I want to classify finite simple groups, right? Groups which have no interesting normal subgroups, right? That's a more tenable problem, and that's been studied in great depth. It turns out that every finite simple group is isomorphic to one of the following groups: the cyclic groups of prime order, the alternated groups of a degree at least 5, the groups of Lie type, or one of the 26 groups called the sporadic groups. Now, the history of this is somewhat involved. This is Wikipedia. History starts at Galois in 1830, right? I mentioned him a little bit earlier. And then you got Cayley defining abstract groups at 1854. Skip ahead a little bit here. Otto Holder proves the order of any non-abelian finite simple group must be a product of at least 4, not necessarily distinct primes. And he asks for a classification of finite simple groups. So it's been in the water since about 1892. Mathematicians have been going, hey, we ought to classify all these, Then Frobenius and Burnside came along, early 20th century, did some really important stuff. Frobenius, everything Frobenius did has his name. So many different things are named Frobenius. Let's see, you're getting to an exceptional. Zassenhaus classifies finite sharply 3 transitive permutation groups. Past this point, there's all kinds of stuff about these. But you look at this, and you should appreciate how much there is that we have not covered, right? I mean, think about this. This is all group theory. This is not elementary group theory. This is all group theory. These are things that have been discovered in mathematics, since the time mostly after the Civil War. Strange term, by the way. This one, Feit-Thompson, the odd order theorem. This theorem alone has a proof, when published, was about 250 pages. One theorem. And the statement of the theorem is not complicated either. Where'd that go? I just lost it. Thank you. This is the theorem. Every finite group of odd order is solvable. 250-page proof.
Solvable.
Exactly. What is solvable? That would be a question for Math 422. Now, I'm not done yet. I'm almost done. I'll get out my system here in just a second. And this goes on until, not that long ago, about the early 2000s, this classification was finally cleaned up. And really, the last sort of awful thing that was done was this monster group. Was one of the things. It's one of these sporadic groups, one of the most horrible sporadic groups. Some guy did this by hand. Grice, I guess, the largest sporadic simple group. It has order 2 to the 46th, times 3 to the 20th, times 5 to the 9th, times 7 to the 6th, times 11 to the squared, times 13 to the cube, times 17 times 19, times 23, times 29, times 31, times 41, times 47, times 89, times 71. In other words, that number. It's about 8 times 10 to the 53 in size. He proved this thing existed by hand in 1982. And if I understand the story correctly, it was known there were computers coming online in a few years. These computers would do it by hand. But no, he wanted credit. So he put his... And the rest, as I understand it, the rest of the group theorists at this time, when they found out what he'd done, were like, why? But anyway, it's a fascinating story. You can read more about it. I'll shut up. Thanks, guys. Oh, group